Welcome back. In the last video, we looked at addition and subtraction examples. In this one, we will look at a couple multiplication and a couple division problems. So note what we were doing in number 3. They're asking us to multiply h, the whole function, times g, which is also a function. So that's h times g. So just like with the subtraction problem, I do recommend using parentheses to separate those two functions. We have our function h, which we'll do in blue there, and g, which is green. And they're asking us to multiply these two functions together. So in order to multiply these two functions, note that they're both binomials, meaning they each have two terms. And we have done this before. We've just never done this in function notation, this whole h times g of x. But the process will be the same. This is a FOIL problem. Taking our first terms, x times 4x, and multiplying those together. Well, x times 4x will be 4x squared. We then jump over to our outside terms, x times negative 3. X times negative 3 is just negative 3x. We have inside terms, 2 times 4x. So if you double 4x, that gives you 8x. And last but not least, 2 times negative 3 will be negative 6. That's just our generic FOIL process for multiplying two binomials. That can happen when you are multiplying functions. We have some like terms we can combine here in the middle. So the positive 4x squared, hanging around, no like terms for him. But negative 3x and 8x, those two we can combine. That will be a positive 5x. And then negative 6, our constant, just tagging along. Note that once again, we don't have to worry about this domain issue. We're starting with a linear function. We are multiplying by a linear function. Both of those have a domain of all real numbers. So this new quadratic will also have a domain of all real numbers. We're going to take a look at a division example now. And with division, we do get some additional domain restrictions, even if our original functions don't start with any. So we're taking a look at f now, and we are dividing f by h. So we take a look at f. F is quadratic. That is our x squared minus 8x plus 4. We are going to divide that by x plus 2. Now, if you look at that numerator, it is quadratic, and usually when we think about quadratics, we think about factoring, what two numbers multiply to 4 and add to negative 8. Well, you can think long and hard about that. You're not going to find two numbers. That numerator doesn't factor nicely, and more importantly, even if it did, x plus 2 isn't going to be one of those factors. So we're not going to have anything cancel here like we did in the rationals unit. We're not going to get anything crazy. This is done with one caveat: restrictions in the domain. We are not allowed to divide by 0, so x plus 2 is not allowed to be 0. A little bit of algebra on that inequality. Note we can subtract 2 from both sides here. So what this really means is that x is not allowed to be negative 2. That is important. That is a part of our solution. It does tell us that. But even if it didn't, keep in mind we're talking about functions here. And with a function, I can substitute any value in the domain. So we can't have values for x that would break our domain. We are not allowed to divide by 0. And when x is negative 2, that makes our denominator 0. So this chunk here in the red box is essential, even if they don't ask for it. So again, when we divide, pay close attention to those domain restrictions. Pay close attention to what's going on in the denominator. Let's take a look at another one. Note that it's two different functions now. We are dividing h by g. So h is the top function. This is division, so order matters. Pay close attention to your two functions. H is x plus 2. That one's in the numerator. And g is 4x minus 3. That one's in the denominator. Once again, we have two functions here. There's no factoring that's going to help us out. Both of these are linear. There's no GCF that they share. So that is done. But again, we divided. So we have to list those restrictions because 4x minus 3, that denominator, is not allowed to be 0. This one is slightly more challenging because it's a two-step equation in order to find out what x is not allowed to be. So we can add 3 to both sides of that inequality, which tells us that 4x is not allowed to be 3. But we don't really care about what 4x isn't allowed to be. We want to know what x isn't allowed to be. So we can divide both sides by 4, which leaves us with x is not equal to 3/4. Again, the reason x cannot equal 3/4 is because if I put that into this denominator, I'll be dividing by 0. 4 times 3/4 is 3, and 3 minus 3 is 0. We can't have that 0 in the denominator. So I started with two linear functions that had a domain of all real numbers, but once I divided them, I introduced this domain restriction. If you're having trouble with those domain questions, definitely raise a hand. Make sure you get those addressed because it's probably the most complicated part of this section. Let's take a look at a really fun one. We take a look at number 6. We're back to multiplication. Hooray, don't have to worry about domain restrictions for these problems. And we're multiplying this quadratic, that's f, times g. Oh, that's 3 terms times 2 terms. If I was writing this out sideways, it'd be x squared minus 8x plus 4 times 4x minus 3. So I'm going to have to multiply 3 terms by 2 terms. We haven't done that in a while, but when we did, this was a problem that we set up using that lattice method. Taking that x squared, that negative 8x, and that 4, creating columns there, taking the 4x and the negative 3 from the binomial, and creating rows. This is just a way to organize our work. You could certainly do this problem without lattice. What's nice about lattice is it lets you know there are 6 terms that I need to worry about. And we'll just walk through those 6 terms as we go. I get an x squared and a 4x. Multiplying those two together gets me a 4x cubed. And then we just move on down. 4x times negative 8x. That's going to get us a negative 32x squared. 4x times 4 gets us a 16x. And then I jump to the next row. Negative 3 times x squared is negative 3x squared. Negative 3 times negative 8x, that's a 24x. And our very last one, negative 3 times 4 is 12. So again, there are other ways to organize your work. We did other methods in that polynomials unit. The lattice one is probably the one I like the best for this big reason. Note that our like terms are down the diagonal here. So I don't have to go hunting through all of my work to find those like terms. We know that 4x cubed is by itself because it doesn't have anything else on that same diagonal. And then as we bump over the negative 3 and the negative 32, we can combine those. That's negative 35. For our regular x terms, we have a 24x and a 16x. That's 40x. And then last, we have that negative 12 tagging along with no like terms. So it's definitely been a while since we had a 3x2. It's interesting to see it pop back up again in this unit. Keep in mind, if you have longer polynomials, if you have 2 trinomials, then you'll have a little bit more work to do than even this. So at this point, if you want to jump on to the next section, watch the next couple of videos, you can. If you want to flip to the practice problems and maybe start the first couple of those to see if you're on track, that's also a good use of time. Definitely let me know if there are supports you need, if there's anything else you want to help make this unit a bit easier for you. And please keep in mind those domain restrictions with division if you are starting those practice problems early. See you next time.